Welcome to qnawire.
In this question, we want to use the uncertainty principle to kind of estimate the energy of electron if it were to be bounded inside the nucleus. So given that the size of the nuclei is about 5 times 10 power minus 15, we can use that as our estimate of the uncertainty in the position given the uncertainty principle is that delta x times delta p greater or equals to h power over 2. We can find the uncertainty in the momentum is greater or equals to h power over 2 times 5 times 10 power minus 15. Right, and this should give us approximately 1.1 times 10 power minus 20 in terms of the SI units, and we are asked to approximate this to be the momentum of the electron. Now we can find what is the kinetic energy of the electron that is confined with this amount of momentum. So the kinetic energy is just the total energy minus away the rest energy. Right, in this case, the total energy, we have to use the relativistic equation, that is p square c square plus m square c4, right, minus away the rest energy. So we can substitute in the values. So for p, this is the value we'll substitute in. C is just the speed of light. M will use the mass of the electron. Right, and that's all the unknowns, all the constants inside this expression, which we can substitute in. Evaluating this in the calculator, we should get about 3.084 times 10 power minus 12 joules. Now, since we want it in terms of electron volts, we can actually divide this by 1.6 times 10 power minus 13 joules per MeV. So this will give us in terms of MeV just 19 MeV. Now we want to compare this with the Coulomb potential energy for a proton and an electron that is separated by the size of a nucleus. And the reason we want to do that is because this Coulomb potential energy is the one that is attracting this electron and pulling it together. So we want to see if this amount of energy is enough to bind our electron into the nucleus, right, based on the kinetic energy which we have previously calculated. So this Coulomb potential energy, take Ke Q1 Q2 over R. In this case, Q1, the charge of the electron is negative E, charge of the proton is positive E. Distance, we're gonna use 5 times 10 to the power minus 15. So Ke is just the constant 1 over 4 pi epsilon naught. So substitute that in, say 0.99 times 10 to the power 9. And we have the elementary charge squared divided by the distance between them. This will give us about negative 4.6 times 10 power minus 14 joules. And if you want to convert this into MeV, again we divide by 1.6 times 10 power minus 13 joules per MeV, and we will get negative 0.29 MeV. Now, based on all these calculations, you can see that if you were to take the total energy of the electron, given as its potential plus the kinetic energy, this will be definitely a positive value, right? Because the kinetic is much larger. Right? Kinetic energy is about 19 MeV, much larger than the potential energy. This will give us a positive value. And this positive value tells us that our electron is not bounded when it is inside the nuclei. Right? It has positive energy, it can escape very easily, and that is because it has such a large kinetic energy that it can overcome the negative Coulomb potential energy, right? Even though there's attractive forces, right, because of the protons, but it is still not enough to attract the electrons and keep them in the nucleus because of its kinetic energy. Right? Its kinetic energy is so large due to the uncertainty principle of the momentum.